Now we have discussed Le Chatelier's principle, and which was that equilibrium would try to counter any change that is introduced into the system, and we are now going to try and understand why it does that. So the first change in conditions is a change in temperature. We're going to see how a change in temperature, the equilibrium would try to, what the Le Chatelier principle states is that the equilibrium would try to counter that change. So equilibrium would try to counter this change. And the way it can counter this change is if we increase temperature, it would try to decrease temperature. If we decrease temperature, equilibrium would try to increase temperature. Now, to understand why this happens, we're going to take an example, and we will try and study the same example that water is evaporating and condensing in a closed container. Let's say I have a container. This is a closed container. This is the bottom of that container, and this container has it has uh, it has liquid water. There are molecules. These blue molecules are liquid water molecules which are close together, sticking together. Because in liquid state you have molecules, they have very high forces of attraction, they are very close to each other. Now this is liquid placed in a container. What's going to happen is that some of the liquid would start to evaporate. It would start to evaporate, and it would form steam. So there would be a molecule of steam in this space in this container. They would be formed as liquid water molecules would evaporate, and this steam, the molecules would be very far apart. So H2O liquid would be converted into H2O gas. And when it does that, some of the molecules in H2O gas would be converting back into, they will be condensing back into liquid state again if they lose energy. So if the liquid molecules gain energy, they evaporate and they turn into steam. Vice versa, if the steam molecules lose energy, they are going to condense and they're going to form liquid water back again. So this process, this side, this arrow over here is called evaporation. And what's happening on this side is called condensation. The reverse reaction is called condensation. Let me write down the reaction in its notation, which is that H2O liquid is forming steam, which is H2O gas, and I'll use a double arrow to indicate that this reaction is a reversible reaction. Now, there's one important thing that you need to know whenever you're dealing with whenever you're dealing with this condition, whenever you're trying to change temperature. Whenever we study the change in temperature, we're going to see which reaction is exothermic and which reaction is endothermic. For example, evaporation, molecules are going to gain energy. So this reaction, whenever you're gaining energy, this reaction is endothermic. Which basically means that evaporation requires energy. On the other hand, condensation is steam molecules are going to lose energy, and when they lose energy, they condense into liquid water. So this particular reaction over here is it's going to lose energy, which means it's going to produce energy. This reaction is exothermic. It's going to lose or it's going to release energy. So let me reiterate. Evaporation is endothermic. Liquid water molecules gain energy and then they get converted into steam. Whereas condensation is it is exothermic. Steam molecules are going to lose energy and then they're going to condense and fall back into liquid state. So we have one reaction which is exothermic and we have another reaction which is endothermic. Now, if I increase temperature, if I let's say I start to heat this container, I start providing this container with heat. So intuitively, you don't need to actually even think. If you start heating a container which has liquid water in it, then water would start to boil or evaporate. It would start evaporating faster. So if you increase the temperature, and we're talking about this, we would build our understanding based on this particular equilibrium. So if we increase temperature, then by just using your common sense, you can figure out that evaporation would become it would become very fast. It requires, because evaporation requires energy. If you increase temperature, you are providing it with energy, and if there is more energy, then more evaporation would take place. So evaporation would evaporation speeds up, and evaporation is an endothermic reaction. So the endothermic reaction is going to be faster. It's going to speed up. Similarly, let's say I put this container, instead of using heat, so instead of using heat, let me rub this off. Okay. Now instead of using heat, I start decreasing temperature. And I can simply decrease temperature by putting this container in a freezer, for instance. So if I decrease temperature, the molecules are going to lose energy very fast, and when they lose energy, then this particular reaction, because if you decrease temperature, you're basically taking away energy, and these steam molecules would start losing energy, and condensation would become very fast. So condensation speeds up. And condensation was an exothermic reaction. So we can say that our exothermic reaction speeds up. Now we will use this information and we will build on this understanding, and we will make a rule based on this, and that rule is uh, rule. Let's say we'll call it. Let me correct this. Okay, let's call it our rule for, or our rule number one, which is when we will deal with the change in temperature. So our rule is, that rule is simply, if you increase temperature, It says this is temperature T degrees centigrade. If we increase temperature, which reaction speeds up? It's the endothermic reaction which speeds up. So the endothermic reaction speeds up, which or we can also say that the endothermic reaction is favored. And vice versa, if we decrease temperature, then our exothermic reaction speeds up. So these are our two basic rules that we will use whenever we deal with a change in temperature. So you shouldn't forget these two rules, which are, so these are first rule which deals with the change in temperature. And let's say we can come up with problems and we can apply this rule to those problems. Let's say I can generalize this now. Let's say I have this equilibrium reaction, which is our first example. You have an equilibrium reaction in which we have N2 plus 3H2, and they are producing ammonia. They're producing two molecules of NH3, which is ammonia. You mustn't forget what ammonia is, because ammonia is going to be frequently used. So you must know what the molecule of ammonia is. It's NH3. And this reaction is a reversible reaction. It is part of a very famous process called the Haber process. So this is a reaction that is given, and to state whether this reaction, which reaction is exothermic or endothermic, generally what they do is that they provide you with the enthalpy change of the reaction. Delta H for this reaction is negative. It's minus 92 kilojoules per mole. Now, what this minus sign means is, if you remember chemical energetics, is and what this enthalpy change signifies is, this enthalpy change is always for the forward reaction. It's given for the forward reaction, not for the backward reaction. So the enthalpy change is negative. It has a minus sign, which means that the forward reaction, this particular reaction, is exothermic. And always the reverse reaction is always the opposite. It's exactly the opposite. So the reverse reaction would be, it would be endothermic. Now, if we apply this rule, the first rule that we studied, the rule, if applied to this, it's going to be, let's say if I increase temperature, T degrees centigrade, then which reaction would be favored? It would be the endothermic reaction which would be favored. So endothermic reaction is favored. Now, endothermic reaction in this case is the backward reaction. Now, there are many different ways to state this. CIE would require certain words that must be used when you're answering this question. So in this case, the endothermic reaction is this backward reaction. So in this case, the backward reaction is favored. Now, since the backward reaction is favored, we can also write, since the backward reaction is speeding up compared to the forward reaction. So since the backward reaction is speeding up, there would be more N2 and H2 that would be formed. So we can say that the equilibrium, we can also write that the equilibrium shifts to the left. Or what we can say is that the equilibrium favors the reactants, because more reactants would be produced. Favors the reactants. Now we'll do another example, and in this example we have N2O4, and this N2O4 is decomposing, and it's a reversible reaction. It can occur in both directions to produce two molecules of NO2. Now what's given is the enthalpy of this reaction is given as it's an endothermic reaction. The forward reaction is endothermic. So the enthalpy which represents the forward reaction in this case is has a positive value, which means that it is endothermic. And when we say it is endothermic, we mean what we mean is the enthalpy represents the forward reaction. So the forward reaction is endo. Vice versa, the backward reaction is going to be exothermic. So I'm going to write the word exo for the backward reaction. So let's say if I increase temperature in this case, if this reaction has reached equilibrium and it's in a closed system and a dynamic equilibrium has been reached, and if I increase temperature, so what the Lee-Chatelier principle states is that the equilibrium would try to decrease temperature. It would try and decrease temperature. It's going to counter that. It's going to do the opposite. And the rule that we stated was that the way it will decrease temperature, if you increase temperature, the equilibrium would try to decrease temperature. It would favor the endothermic reaction. Which in this particular case happens to be the forward reaction. So the forward reaction would speed up. The forward reaction is favored or what we would state is that equilibrium shifts to the right. Shifts to the right. So our forward reaction is favored, which is this endothermic reaction. Vice versa, if I decrease temperature, then if I decrease temperature, so if I decrease temperature, let me move the page upwards. So if I decrease temperature, then the equilibrium would try to do the opposite, Lee-Chatelier principle. It's going to try and increase temperature. It tries to increase temperature, and the way it would do is if you decrease temperature, and if you remember the rule that we studied previously, if you decrease temperature, then exothermic reaction would be favored. Is favored, which in our case it happens to be the exothermic reaction. Let's go back to our equation. The exothermic reaction happens to be the backward reaction. So we would be talking about this particular reaction, which is in the backward side. So the backward reaction would be favored. So what we're going to say is that backward reaction is favored, which in other words would mean that equilibrium shifts to the left hand side. Or we can also say that equilibrium shifts to favor the reactant side.